Okay, so let's continue with our binary search playlist. But before that, hey, welcome back to the channel. I hope you guys are doing extremely well. So the problem that we're going to solve today is finding a peak element, the second. Now, before watching this video, please go back in the playlist and watch the part 1 where we have figured out the peak element in a 1D array. So what does this particular problem state? It states that instead of a 1D array, it will be given a 2D array. And it is clearly stated that none of the two adjacent cells will be similar. What does that mean? If it is 2, it cannot be 2, it cannot be 2, it cannot be 2, it cannot be 2. So the problem is stating you're given a 2D matrix where none of the two adjacent cells can be similar. Your task is to figure out the peak element. And the part 1 of the problem, we had a 1D array where the peak element was an element that is greater than its left counterpart and it is greater than its right counterpart. So any element that was greater than its left and greater than its right was called as a peak element. Now in this particular problem, since a 2D matrix is involved, we will call an element a peak element only if it is greater than its left counterpart, greater than its right counterpart, greater than its top counterpart and greater than its bottom counterpart. For an example, I can say 9 as a peak element. Why? Because it's greater than its top counterpart, greater than its right, greater than its bottom, greater than its left. Can I say 7 to be a peak element? Yes, I can say 7 to be a peak element. Why? Because 7 is greater than 3, the left, greater than 1, the top, greater than 2, the right. But on the bottom, we don't have anything. If you do not have anything, then it will be considered as -1. So the problem is clearly stating all the outer parts will be having -1. So thereby 7 can also be called as a peak element. Now in a 2D matrix, there can be simultaneous, like there can be multiple peak elements. Your task is to return the row and column of any one of them. Yes, any one of them. For an example, you decide to return this peak element. It is on the row 1 and it is at the column 1. So you'll have to return 1, 1. In case you decide that you have to return for this one, so it's on the 3rd row and it's on the 4th column. So you'll have to return 3, 4. So this is what the problem is stating. Now, if this problem comes up in an interview, what is the first solution? The first solution that I can think of is like the extreme brute force. I scan through every element. Yes, I will be scanning through every element in a 2D matrix. And whenever I'm standing at an element, I check for its left counterpart, check for its top, check for its right, check for its bottom. If it is greater than all the 4 counterparts, I will be calling that element as a peak element. So if I'm scanning through every element, what can be the worst possible scenario? I'll be scanning through every one till the last element, isn't it? So it will be n cross n because that is the number of elements in the 2D matrix. And if I'm checking, whenever I'm standing on an element, I'm checking for 4 directions. So for every element, I'm checking in 4 directions. So can I say that the overall time complexity, the worst possible case will be n cross 4? I can, right? Can I optimize this? I can, but by a slight margin. Now, for the best possible case, it will be, you just find out the first element to be the peak element. On an average, it will be somewhere in between. Only in the worst case scenario, the last possible element will be your peak element. And that is when this particular complexity will appear. I can only optimize the worst case scenario. I cannot optimize the best case. I cannot optimize the average case. I can definitely optimize the worst case scenario. How? Can I say, if I just return the largest element in the matrix, that will be my answer. Over here, 9, 9 is the largest. If I simply return 9, that will suffice. So if I go by the approach of finding the largest element in a 2D matrix, even in the best case, I'll have to scan through every element from the first to the last. Even in the average case, I'll have to scan through every element. Even at the worst case, I have to scan through every element. So the complexity will boil down to n cross m, but this will be a complexity for best, average and the worst case complexity. So not that much of optimizations. Now, will this be accepted in an interview? No, they'll ask you to optimize this. So you've been asked to optimize n cross m. In this particular problem, we have a 2D matrix and the total number of elements in the 2D matrix is n cross n. So the algorithm that we have figured out is equivalent to the search space, right? So we're searching for a peak element and they're asking us to optimize. I cannot go through every element because if I've been asked to optimize n cross m, that technically means I have to trim down n cross m, which means I cannot go through every element. If I cannot go through every element, which means I have to delete, I have to skip some portion of the search space, and that is when you start thinking of algorithms, and that's when binary search comes in, because searching algorithm cannot go through everyone, have to skip. I think binary search is a potential candidate, and I start thinking in the direction of binary search. So before I move on to the binary search approach, please make sure that you should have seen the part 1 of this particular problem. In case you haven't seen it, or in case it has been a very long time, please pause this video right away. Find the link in the description, go back and watch it, get the intuition again back in your head, and then start watching it, because whatever intuition I've used in the part 1, I'll be reusing that over here. So if you remember, in part 1, I stated this thing that we're going to use binary search. And whenever we are standing on the mid, that mid will be the peak element only if it's greater than both of its left and right counterpart. And that is very obvious, because if you're standing at a peak and it's greater than left and right, that's a peak element. You stop. But in case this mid element was smaller than the right part, which means, imagine you're standing here and the right part, this is the right part, so it's smaller than the right part, which means there is definitely a peak. There is definitely a peak on the right. Just think it as a mountain range. If you're standing here, the mountain has to go up before it goes down. Somewhere it will go down, because it is clearly stated outside of the array, it is -1. So even if it doesn't goes down, I'm very sure there will be a -1 at the outer portion of the array, because that is stated. Thereby, whenever I'm standing here and the right portion is actually greater, I eliminate the left half, right, in the part 1. And similarly, if the mid is smaller than the left, which means you're standing here, yes, you're standing here, and this is your left, and it is smaller than the left, thereby I'm very sure that this is the inclination of the mountain. Thereby, you delete the right half. This is the intuition that we followed in part 1. We'll follow the similar intuition in part 2 as well. So let's try to solve it. What I'll try to do is, I have 6 rows. I'll take low to be standing at the 0th row and the high to be standing at the 5th row. I'll try to have the algorithm. What is mid for the first scenario? The mid will be 0 plus 5 by 2. That's the second row. Which is the second row? Can I say this is the second row? Tell me one thing. In the second row, which element has the highest possibility of being the peak element? Just think. Can I say whoever is the largest has the highest probability? Yes, someone else might be, but who has the highest probability? Can I say 6 definitely has the highest probability, because that's the largest element? So I'll be like, okay, fine. Who's the max? Max is 6. Where is it? Here. Let's see if this can be a peak element. I stand at 6. It's greater than all its 3 counterparts. But it's not greater than its left counterpart. Thereby, 6 cannot be a peak element. Hence, you say that 6 cannot be a peak element. Now you need to omit some portion, because 6 can never be a peak element. And if you go on checking every element, you will not be able to optimize. So you don't go and check every element. You check for 6 and you say that this is not my peak element. Now the question arises. You took 0 and 5 to be low and high. Now you're standing at second column. Do you delete the left half or do you delete the right half? Is the question, because that is how we have been doing binary search. Let's start going back to this particular intuition. And I think, hey, listen, why is 6 not a peak element? The only reason is there is someone on the left who is greater. There is someone on the left who is greater, right? Can I say, if this is 6 and this is 7, is someone on the left who is greater? So maybe delete the right half. Yes, I go ahead and I say, delete the right half. Yes, I delete the right half. The moment I delete, the high will, the high will come here. Yes, so low will be at 0, high will be at 1. Let me quickly erase it. So can I say low is at 0 and high is at 1? Thereby the mid will be 0 plus 1 by 2. That's 0. So if the mid is 0, who has the highest probability? Again, technically if I take the max element, that will always have the highest probability. And 4, yes. Now I see 4 is greater than its left. 4 is greater than 2. 4 is greater than its bottom. And at the same time, 4 is greater than its top. Thereby I say, the max element 4 is my peak element, and we stop. Yeah, I know 9 could have been an answer, 7 could have been an answer, but we figured out an element, and that is what we require. Just one, and that is where we stop. So part 1 was simple because it was a 1D array. It was easy to visualize. In the part 2, you might have a couple of questions. The first one is, why are we taking the max element? And the second one might be, I'm not sure if you have this question. You said 6 is not the peak element, and you eliminated the right half and you moved left on the basis that 7 is greater than 6. Thinking that 7 might be your peak. But wait. 9 might be my peak. 7 might not be, because 7 is smaller than 9. So how are you managing this vertical alignment? Not vertical. How are you managing this alignment? Whatever it is. So let me first answer this question. Why am I taking max? So whenever I'm taking an element, when do I call it a peak element? If it's greater than its top, greater than its bottom, left and right. Now if I'm taking max, in this case 6, am I very sure that it will be greater than its top and bottom? I'm very much sure about it. I'm left out with 2 cases, which is the left and the right. That's what I have to check. That kind of boils down to a 1D array case, because I don't need to check for these cases. Kind of boils down to a 1D array scenario, right? That is why I'm taking max, because I'm trying to go in the direction of 1D. Got it? Now the second question comes in. But Shriva, then how do you manage 7? Because it has a vertical alignment as well. This is what I'll now explain. Tell me one thing. If 7 is greater than 6, I'm saying 7 might be my peak according to the intuition. Thereby I'm going left. 7 might be my peak, but 7 is not. There's someone 9 which is greater. Tell me one thing. If 7 is greater than 6, which technically means, I repeat, 7 is greater than everyone here, right? Hence, 9 is also greater than everyone here, right? Hence, 9 is also greater than everyone here. Indeed, because if 7 is greater than 6, anyone greater than 7 will also be greater than this. Hence, this alignment is maintained. Even if you cancel off everyone, you're considering, I'm not saying 7 is definitely my peak. I'm considering it to be my peak. And if it is not, if someone else is greater than 7, it will always be greater than its right part and the bottom part. I just need to check out the other parts. And eventually the algorithm will flow. You can take a bigger matrix, but just think on it. You'll start understanding it. The core is, if the intuition for the part 1 is crystal clear, you'll understand this as well. So as usual, I'll be writing code in pseudocode. I'm not sure why people on Twitter, on LinkedIn say that my course is in C++. I don't write code in C++. I write pseudocode. You have to understand this is pseudocode. This is not C++ Java. Please, if someone is saying I teach in C++, correct them. Tell them that Raj teaches in pseudocode version. And then you can write any code in any language. Got it? So we'll be writing the code. So I have a function which is given a matrix, and assume it's given an nm. If not given, you can find it out. Can I say the low will be 0 and the high will be the last column, which is m minus 1. Very much sure. Let's quickly write down the binary search. The binary search will go from low lesser than high. Correct? What will I do? At the first time, I'll do low plus high by 2 to get the mid column. Can I say this will be the mid column? Now, what am I doing? What am I doing? I'm trying to figure out where, like at which row is my max element. Figure out that row now. Figure out the row where your max element is. Maybe write a function which gives you the max element. Send them the matrix. Send them the n, m and the column number. So, I think you can write a function that returns the row number. That returns this row number 2, stating the row number 2 as the max element. You can do that, right? So, I'll write that. I'll show you afterwards in case you cannot. So, I have the row, I have the mid. What is my next job? To check the left and the right. That's what I have to check. Can I say on the left, what will be left? What will be left? Think. It's on the same row. So, if I'm standing at mid, the left will be mid minus 1 and the right will be mid plus 1. Very obvious. So, I'll take the left and I'll take the right. So, I'll be left. Left, can I say that if mid minus 1 is greater than 0, in case, I can easily take the left to be whatever row we are at and mid minus 1, or else we can simply say minus 1 because that's a small number. On the right, if mid plus 1 is still lesser than the boundary, in that case we can take matrix of row of mid plus 1, or else on the outer part we will always take minus 1. So can I say if my value at matrix of row and the mid column is greater than left and greater than right, can I say this is my peak element? Yes, I can. And thereby you can always return the row and the mid as the column. Perfect. Else if the matrix is smaller than the left, which indicates the left one is greater, there is a possibility that the peak is on the left. I say high equal to mid minus 1. Or else I will go the opposite, saying low equal to mid plus 1. That's how it is done, because if this condition is false, either this is false or this is. That is how it is done. If this if is false, which means either this is false or this is false. So we just check for else if, and the next else will be following. And at the end, you can just give a dummy return of minus 1. Why? Because it's a function. It will be expecting you to return something. So just give a dummy one. So in all the cases, you will be finding a peak element. That is what the question is stating. So don't worry about this. This is just a dummy line that you have to write in order to complete the execution of code. So let's quickly jump into the code editor. You can find the C++ code on the screen. In case you want the Java, Python and JavaScript code, the article link will be in the description. You can definitely check it out. I am opening this because I wanted to show you how to find the max index. It's very obvious. Just go through this entire column, which is having n rows, and then you figure out whatever is the max value, you store it. At the end, you return the index. Pretty simple. And apart from that, everything is self-explanatory. We have written the same on the iPad and we're returning the dummy. What I'll do is I'll quickly go ahead and submit this. What will be the time complexity of this? I'm doing a binary search. So can I say I'm doing a binary search on the number of columns? I can. So what will be it? It will be logarithmic base to m for sure for binary search. And on every binary search, I'm scanning through entire column to find out the max. So the column length is n. Can I say BGO of n into logarithmic base to m is my time complexity? What about the extra space? I'm not using any extra space. So BGO of 1 is my space complexity, and this will be the most optimal solution. So this will be it for this problem. In case you've understood the entire intuition, the solution, please do consider giving us a like. And if you haven't checked out our merchandise store, the link will be in the description. And yeah, if you're new to our channel, do consider subscribing to us. If you haven't followed me on Twitter, Instagram, LinkedIn, all the profile links will be in the description. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye-bye. Take care.
Whenever your heart is broken, don't